Here's an example of free undamped vibration. We've got a mass here of 2 kilograms with a stiffness of a spring of 8 newtons per meter, and we have some initial conditions as well. The initial position is 1/2, so I've got that drawn over here where the starting value, the starting position, is below the equilibrium position. So it's been pulled down, and then the initial velocity is +1, so it's moving downward at the beginning of the problem, assuming we're counting y downward. So there's our setup, and we can quickly put in the values from the model earlier. So we have our omega is the square root of k over m. So that would be the square root of 8 over 2, which of course is 2, and that's measured in radians per second. Again, that's an angular velocity, and it's related to the cycles per second by a factor of 2 pi. So then our function that describes the position of this mass over time as it relates to the equilibrium position, y of t would be c1 sine of 2t plus c2 cosine of 2t. Now, if we want to find out what C1 and C2 are, as always, we're going to use these initial conditions. So we're going to first use y of 0, so it'll be 1/2 equals C1 times the sine of 0, which is 0, plus C2 times the cosine of 0, which is 1. So C2 equals 1/2. And then if we take the derivative, y prime would be 2c1 cosine of 2t minus 2c2 sine of 2t. And then doing the same thing with the initial value of the derivative, 1 equals 2c1 times cosine of 0 is 1, minus 2c2 times sine of 0, which is 0. So 2c1 equals 1, which means c1 also equals 1/2, which means our final model is y of t equals 1/2 sine of 2t plus 1/2 cosine of 2t. The other way to write this, of course, is to use the alternate formulation where you have a sine of omega t plus phi. And again, don't forget the connection between these is that a is the square root of c1 squared plus c2 squared. So in our case, a would be the square root of 1/2 squared plus 1/2 squared. 1/2 squared plus 1/2 squared, that would be 1/4 plus 1/4, or 1/2. So the square root of that would be 1 over root 2. Then phi is related to c1 and c2. The tangent of phi is c1 divided by c2. Since they're equal, that's 1. So tangent of phi equals 1. The simplest value to use for t, or for theta rather, for phi, would be pi over 4. Of course, you could use other values and it would just be a shifted version of this, but the easiest one to use is the first value that comes to mind, which is pi over 4, rather than going around the unit circle again. So the alternate way of writing y of t would be to write 1 over the square root of 2 sine of 2t plus pi over 4. And again, whichever one's more convenient for a particular question is the one that we'll use in that moment. So let's ask a question that you might see on a homework problem, for instance. Question might ask, when does this mass pass through its equilibrium position? Now, of course, if you think about this, it's going to pass through the equilibrium solution many times. In fact, it's going to pass through it infinitely many times. Because there's no damping, it's going to keep oscillating back and forth around this center line position. So when we read the question, when does it pass through for the first time, we're going to interpret that as, when does it pass through for the first time? What's the first time that it passes through the equilibrium position? So it boils down essentially to solving where y equals 0, because that's the equilibrium position. So we're solving essentially the equation that looks like this. Notice, by the way, I'm using the second formulation here, just because it's going to be a little bit easier to solve for. Since there will only be one trig function, just the sine, a single sine function, is easier to solve for than if we've got an equation involving both sine and cosine. Of course, we could solve it that way, but this one just might be more convenient algebraically. So as I said, use whichever of these is the most convenient in the moment. When we're solving something like this, it turns out this version is a little more convenient. So if we work on solving this, we can multiply both sides by the square root of 2 to get rid of this, which just means that all this has to equal 0 as well. So it basically simplifies to this equation. And so if you think back to your pre-calc days, to solve something like this, where we're looking for solutions to a sine function, we have to think about where does the sine function equal 0. The sine function equals 0, if you look at a graph real quick, looks like this. So it equals 0 at 0 here, at pi, at 2 pi, at 3 pi, and then over at negative pi, negative 2 pi, etc. So the sine function equals 0 at any integer multiple of pi. So to write that down, we're going to say that this input to the sine function has to equal n times pi, where n is an integer. So again, this happens infinitely many times. For any integer value, it's going to pass through. We're going to assume for a minute that we're not allowing t to go negative, so we'll cut off some of these, but we're looking in short here for the first time it passes through. So to solve this, we can rearrange to solve for t. So we'd have, well, for the first time, would be when n equals 1. So we'd have 2t, well, let me do it this way. Let n equal 1, which simplifies so that our answer doesn't involve an n. That's all it does. It makes it a little bit easier to work with. So then we can subtract pi over 4 from both sides. So we get 2 pi equals 3 pi over 4. And then divide both sides by 2. So t equals 3 pi over 8. So there's the t value the first time this passes through at t equals 3 pi over 8. This is the first time that it passes through the equilibrium position, or the line y equals 0.